This is the attention mechanism in the transformer architecture. Everyone loves it. I love it too because I tried it on one of my projects. It ended up working very well. I thought I can design a convolutional neural network that could capture all the inductive biases that I would know it's only sensitive to the neighboring local tokens. It ended up finding that there is actual interaction between one token and another token very far away in the same sequence. And that is great. That improved the model performance. But at the same time, that does not come for free. Because to find those correlations or interactions, I have to query every token in the sequence to every other token in the sequence. And in doing that, the computational complexity is high. If you have n tokens in the sequence, then the computational complexity is n squared, which is usually known as the quadratic computational complexity of the neural network architecture of the transformer. This obviously has been an issue because it's very expensive, especially during inference that you have to wait for token by token and you can't easily parallelize it, and that's causing a problem. So people have been trying different ways to resolve it. Here's a reformer neural network architecture. They have this locality sensitive hashing method. So we constrain where we're looking when we're doing the attention in a sense, and therefore it's more efficient. There is a sparse transformer by OpenAI. They also constrained how many other tokens the token is going to look at in doing the attention, and therefore made it cheaper. There's this big bird by Google. They're saying that, well, not really every token has to look globally. Some tokens can just randomly do the attention operations. Some tokens, I'll just do a window, maybe for in and at and on. For those conjugate words, we can find a narrow window. Maybe for some words, we have global attention. Maybe they're in the beginning of the sentence. And when we mix those three, we got the big bird mechanism. And also there's, I think, more traditional long-former. We have the full attention, and of course we can do sliding window attention, a little bit like a CNN concept. We can have a dilated sliding window, a little like a dilated convolutional layers, and we have a combination of global plus sliding. So all of those work, I think, reasonably well. They're all doing a similar thing, in my opinion. They're kind of trading off the computational complexity and the model performance or accuracy, in a sense. And they work well, and they might be the ultimate answer. But if you're like me, you might be thinking that, well, can there be actually one neural network architecture that was born without this quadratic computational complexity? And maybe there is another way. It doesn't have to be better from the beginning, but is there something else we should be looking at? And this is exactly what Albert Gu and Chai Dao, they were thinking probably. They were from Carnegie Mellon and Princeton, and they wrote this famous paper a while ago called Mamba linear time sequence modeling with selective state spaces. It's a selective state space model that is actually a very strong contender. And in my opinion, probably people would unanimously acknowledge that this is the only powerful serious contender for the dominating transformer neural network architecture. So I will try to, in this video, do a short introduction to this architecture and have fun in learning more about it. So let's recall what the problem is that we're trying to solve. We're saying that there is this quadratic n squared time complexity of the self-attention mechanism in the transformer architecture. What that means is when I have one token, I need to calculate the attention for every other token in the whole sequence. This is actually a bigger problem during inference time, because in inference time, when we are trying to generate the fifth token, I need to know the first four tokens, and there's no way before I generate the fourth token that I know what the first tokens are, right? In the training process, it is still n squared, but at least I can parallel process it, because in an autoregressive training task, I already have the label, and I can do it in parallel. But in inference, I can't do this. But you actually recall, in inference, we have some other models that's very well founded in the history that is called RNN, right? We have the LSTMs, the GRUs that do similar things. That it is actually when I'm generating the next token, I only need to look at one token before it, which means that I can do only linear time complexity. I don't need to look all the way behind me. I just need to look at one immediate token behind me. So that is actually very efficient during inference time, with the only problem being that in training time, this cannot be parallel processed because I don't know the hidden state before I process all the previous tokens. So in this paper, the authors propose something very similar. If you look at the diagram, the top ones are the RNNs we already have for a while, and the lower ones are the state space models over here that looks very similar, right? Except for that I'm adding all these capitalized letters like A's and B's over here that looks like a matrix, right? Capitalized bold letters. And yes, there are matrices and there are matrix multiplications. And you might ask, hey, what difference does it make? In the RNN, we can just put it in the cell, right? Well, actually, this makes a huge difference. By formulating, in my opinion, this RNN cell in a very special way, we can actually benefit from both the inference time and the training time. We can both enjoy during the inference time the linear time complexity, and in training time, we can parallel process it in a way. And let me show you how. And by the way, a big shout out for all the visualizations here. I am stealing them from Maarten's blog, and he's done an amazing visualization over here. I posted the link down there, and if you want to take a look at his blog, I think it'll be very worth your time. So here, this theory actually stemmed from the control theory of continuous time system. You can tell there is this input X, and this X impacts the hidden state H in a way. Of course, there's a B matrix to project it, but X impacts H. And also H from the previous time impacts itself. Of course, it's after projection of A, but it's impacting itself. And after that, H will project back to the output Y. And of course, maybe we can choose to have X to also feed directly to the Y by a projection of D. So this is a continuous time theory. Then from this continuous time system, we can derive actually two inference methods. One is recurrent to calculate Y from X. That is very linearly efficient in inference time. And we can also do it in a convolutional way, which means that we can parallel process in a very easy manner. So how do we do this? If you don't mind, let's do a little bit of math derivation. This continuous time system can be described by these two equations. One saying that the hidden state, how it updates itself, is going to be impacted by itself, and the input, of course, both projected. And the output is simply its hidden state projected plus the input projected. And now with this continuous time equation, we can actually get a discrete form of two kinds. One for recurrent inference, that we can say, well, the hidden state at k plus 1 time is simply a matrix multiplied by the hidden state at time k plus input at time k projected by another matrix. And we can know these A bars and B bars from the continuous matrices of A and B and this discretization time step delta. And once we know that, we can have yk is basically the hidden state projected plus, again, the input projected. This is very linear because you can see that, unlike the transformer, we need to look at all the other tokens in the sequence. For the h of k plus 1, we only need to look at one time step, which is hk. So this makes it linear. And we can also have a convolutional mode, if I may call it, because it can make the inference much faster. The equations will look like this if we come from here, that the yk is a convolution, right? We can have this k bar entry where, k bar of j and x of k minus j looks like a convolution, typical convolution, right? And the k bar can be calculated in this format. And then you can see that this is easily parallelizable. If you write out the whole equation, you can see that we can actually write it in the form of a multiplication, element-wise multiplication of two vectors multiplied. So this can be very fast during training time. So how do we derive it? Well, I'll go through a little bit of math over here, and I think you'll actually enjoy it. These are the equations we're starting from. If you recall your ordinary differential equation classes, this is actually pretty classical. We just rewrite the first one, the h prime, into dh over dt. We just pull the dt onto the right-hand side and do an integration. And in the integration, we set the lower limit to be k delta, which means the k is time step, right? And the upper limit to be k plus 1 delta, which is, the next time step. And we'll just integrate these. On the left is just ht being integrated, so we can see it's simply h of the next time step minus the h of current time step. In solving these, we can probably recognize that from the ODE class, this solution is going to be formed by a homogeneous part and the particular part. For the homogeneous solution, we say, well, A is mainly how the hidden state itself impacts itself. So we can, for now, just ignore the input term bxt, and we just write this one. And you can guess, actually, this is how the textbook does it, you can guess this looks like an exponential function. So we have this exponential function that we guessed. If you don't believe me, you can try to plug it back in. It actually works out. Once we write this out, we can just replace the t with the k plus 1 delta, because that's the one we're using in the integration. Then we can write this exponential term out, and we plug it back in. Once that we plug it back in, we can see that the left term is actually easily evaluated, because you can easily integrate an exponential form in the analytical format, right? We have a closed form solution, we can write it out. Notice that, we have the h of k delta over here, we have the h of k delta over here. It'll make us a little bit convenient in the future. But now let's look at the right-hand side term first. This term is a little bit tricky, and if you don't remember what a particular solution is, you probably can refer back to your textbook. Very briefly, because we already know the homogeneous solution, when integrating this over time, we know we can actually left multiply a term of the exponent of k plus 1 delta minus tau, and we replace those t here to be taus. And if we exchange a variable for this k delta to be 0, the k plus 1 delta to be delta, and we over here can get this very simple exponential term over here. We also do another thing called zero order hold to simplify this evaluation. We just assume, well, xt is changing not that fast, that between k delta and k plus 1 delta is going to hold the value flat at k delta. So the b times x of k delta is constant during this integration, so we can plug that out. And once we do that, we can evaluate this term to be like this. And now we have this very simple exponential term. We can evaluate it analytically, and we can get this evaluation from the top over here. We solve this one. Now remember, we actually have something very close, or exactly what we're looking for. We want to write the hk plus 1 to be a form of hk plus xk. We just rewrite this term as just hk plus 1. This is exactly hk. This is exactly xk. We just call this term over here a bar, and the other term b bar, and we have this formula. We can use this formula to solve in a recurrent form during inference that is linear time complexity. So this all works out. And you might ask, hey, Shawn, didn't you say that we also have a convolutional mode? Yeah, it's actually very simple. In deriving the convolutional format, recall that we have yk equals to c times hk plus c times sk. Now, we know what hk is, right? From the last page, we know that h1 is basically a bar h0 plus b bar x0. We can continue that. h2 is a similar thing to h1. And because we already know h1, we can plug it back in. So we noticed that we need to multiply the h0 by a bar twice, and we need to have this x0 times a bar b bar and x1 times 5b bar. We kind of see a trend over here, right? So if you just continue to plug everything in, you will realize that hk is basically a bar raised to the power of k times x0 plus a summation of a bar raised to sum of the power times b bar times xj. So if we organize a little bit, we can plug it back in to say, well, y bar is basically c times this huge thing plus d times sk. Because h0 is initial state, we can just simplify by saying, well, initial is always 0. We can do that. We just cross this term out. We have this yk equals to this long equation of evaluation, where if we just organize, we can get to the format that we were talking about, that this is a typical convolution that we can easily parallelize. You might say, hey, Shawn, are we here already? This is too good to be true. We can easily benefit from the linear time complexity that transformer doesn't have, but at the same time, we can parallel process it during the training time. This is not that complicated. Why didn't people do this simpler thing earlier? Well, actually, you're right. This is too good to be true. One thing you can notice from this system is that it is called linear time invariant. that these A and B and C and D, these four matrices, they don't change over time, which actually limits their capability. So the authors of this paper actually raised a few good examples. So for a copying task, for example, if I'm asking the model to copy, can you copy these four tokens that a while ago showed up? This model can totally do that because it is linearly time invariant. We don't need to know what actually happened before. We just need to know we need to copy those. But if we have something called selective copying, which is saying, hey, model, can you copy those colorful tokens over here? That means the model needs to do things differently if it's of color blue, orange, red, or green, versus just blindly copying things. But these A and B and C and D, they are not that complicated. They can't change their own behavior based on their input values. And therefore, if you're trying to apply this LTI, linear time invariant model, they won't do that well. Similarly, there's this induction heads task that, hey, if you see the black token, can you let me know what's the token right after the black token? That means the model needs to see the black token and know, oh, okay, I need to be alert. And I need to change my behavior to remember the next token right after the black. This is also not possible by the linear time invariant model. So one obvious solution here is, why don't we make those parameters dependent on the inputs? And this is exactly what the authors did. So for the previous model, we call them S4. We have the matrices of A, B, and C. Just a quick recap. A is how the current state evolves over time. B is how the input influences the state. And C is how the current state translates to the output. They are all of dimensions of n times d, where n is simply the hidden state size, how many dimensions we have in the hidden state, and the d is just the size of the input vector. And we also have the input xk and yk, where within a batch we have a number of inputs, and every input is of length of the sequence times the d, the dimension of the input. So the authors say, well, you know what? Let's make these new matrices dependent by what we're seeing in the input. So this is what they did. They made three variables, the step size delta, the matrix B, and the matrix C, all input dependent. So actually, you may notice, if you want to make it input dependent, it should be a dimension of B times D times L times N, which is pretty big, right? So the authors say, why don't we divide and conquer? For the step size delta, you're going to be just B times L times D. And for the hidden state dimensions, you don't have to customize for every different channel in the hidden state. And you leave that task to the matrix B and C. The matrix B and C are going to be B times L times N, but they're not being customized to the input dimension of D because that task is being handled by the step size delta. And because we need to convert all those continuous time matrices to the discrete time, if you do the math, the A bars and B bars are still of the dimension B and D and L and N. This is the original algorithm block they showed in the paper that you can see compared to the original S4 linear time invariant model. In the new S6 model, what they're doing is, instead of having those matrices of B and C and delta as constant, actually delta is a vector, they are going to do a linear projection of the input X to form a bigger B, a bigger C, and also a bigger delta. In the delta, they actually applied a soft plus on top of it. And then they formed the A bar and B bars to be B times L times D times N, which is fully customized to the input. And before it's time invariant, we can do recurrence and convolution. And for the time variant, we have recurrence scan only. And they'll say, hey, Shawn, hold on. Isn't this defeating the purpose why we're doing this here? Indeed, all the reasons that we're doing this here is because we thought state space models can do something that neither the transformers or the RNNs can do, which is we have this linear time complexity during the recurrent mode, during inference, which we still seems to be able to do, right, step by step. But are we compromising the parallelized capability of the convolutional mode? Because don't we still have to calculate the previous tokens before we get to the next? Are we going back to LSTM? Well, I think there's a very important thing that the authors did that made all these different. It's that, if you recall, for LSTM, it's not only dependent on the input is also dependent on the hidden state, right? But for the safe space models here, we just say it's dependent on the input, not the hidden state. And therefore, we can leverage a parallel scan algorithm that is not as good as the pure parallelization, but it's still pretty good. The parallel scan algorithm is well founded in the computer science domain, that you can think of it as, well, even though we can't get the full output before we know the previous hidden state, that is true, we can still do something because the B-bar matrices are just dependent on the input. So we can still pre-compute the B times X for a lot of the computation, and then we just combine them a little bit later. So the parallel computation can be of a time complexity of O of n divided by t. In addition, the authors added more acceleration that is about the hardware part. The GPUs actually have two sets of memory. There is this static RAM, and there's this high bandwidth memory. The static RAM is actually pretty small, but they're super fast, and the computation heavy part is probably better done over here. And there is this bigger part that is a bit slower, which is called HBM. Well, the authors say, well, the hidden state is pretty big, and we want to do a lot of computation over there, so we're going to be storing the hidden state in this orange color area, which is static RAM, and we're going to do all those computations using the static RAM. And for those a little bit of slower is okay part, we're going to use the HBM to do those. And by doing this, we're also minimizing the data transfer back and forth between the SRAM and the HBM, which is very expensive. The one last trick I want to talk about here is the HIPPO that the authors use. HIPPO stands for high order polynomial projection operators. So what it does is we're trying to compress the input signal somehow into the memory, right? The input signal we want to compress in a way that we value more of the information that just happened about right now. And we probably will try to forget some of the things because we have limited memory, want to forget some of the things that happened a while ago. So the HIPPO operator do this compression methods. And how they did it is they initialize the A matrices using HIPPO. They choose the values in the A matrix as the legendary polynomial coefficients. Legendary polynomials are those orthogonal polynomial bases, that is orthogonal only within the biunit domain, -1 to +1. They use a similar idea, and by initializing those A matrices using HIPPO, they can actually make the model performance much better. And here we are. Finally, we are at the Mamba block. The authors learned from H3, which is a very typical SSM model architecture. They do some projection first, and with some projections, they run the convolution. They combine them, they run the SSM, which is usually linear time invariant over here. They combine the third block over here, and then do another linear projection, and that's a block, a little bit like the transformer block. They learned also from the gated MLP some of the tricks, and they combine them into the Mamba. What they do is the input tokens come in, they linearly project it to a higher dimensional space. On one branch, they run this convolution with the neighboring tokens for some local sensitivity, maybe for words like in and at, you want to be looking at a few neighboring words. And you run a CILU activation. You run through this SSM that we've been talking about that is actually time varying. That's no longer linear time invariant. And then you combine that with the other branch, which is simply projected to a higher dimension, pass it by CILU, and then multiply together over here. Then you do a linear projection over here down to the original dimension, and that's a whole Mamba block. And thank you, Maarten, again for this amazing visualization, that this Mamba block is repeated n times. And also, in the original plot from the paper, the author seems to be forgetting a skip layer connection, which Maarten kindly added. And we repeated n times. Eventually, we are going to pass the output through an RMS norm, which you can think of it as like the batch norm, layer norm we're doing. It's just that it's normalizing all the activations by the root mean square of them. And then we run another linear layer plus soft max, and we're choosing the words of highest probability, however you sample that, to get the output. So how does it perform? Actually, I think we're perfect at time because I made this video on today is August 17th, and 5 days ago, August 12th, a model called Falcon Mamba was released. Of course, you can see the benefit over here. Mamba, you can actually do infinity context window because you just need to keep going, right? There's no storage limitation in the GPU that we could impose over here. And they say, well, even if we don't do this sequential prefill mode, they do this parallel prefill, which is for the prompts, we want to parallelize the processing of it such that we're faster. And because we're parallel processing it, we are limited by the memory we have in the GPUs. They have a single 24 GB A10 GPU, and they say, compared to Llama 3.1 billion, which is 1 billion more parameters than the Mamba, they can still have higher context length. And if you look at other behaviors, you can see that when we're increasing the context window, the throughput of Mamba is very stable. It doesn't drop at all. While for transformers, you can see that it's starting to drop off during the throughput because the context windows are longer. And if you look at the memory consumption, Mamba just have a constant memory consumption. While you can see for Llama, you can see an increasing consumption of the memory. And of course, all of these wouldn't help if their accuracy is dropping a lot, right? So they actually also tested the accuracy. This is a result of a lot of different tests. For example, this math level 5 is they're comparing the performance of Mamba in math compared to other models like Llama or Mistral or Falcon 2, their own transformer-based model. I would say the Mamba is not necessarily the best in every task. For example, in this math task, it's not as good as Llama, or if it's in this MMLU, this language understanding task, it's actually the worst of all. But you can also see that in many other tasks, it's actually better than the others. So on average, well, of course, it depends on how you weight it. In this naive weighting, the authors claim that the Mamba model is the best, of course. What I want to say is, I don't want to say Mamba is absolutely the best and we're going to take over the whole transformer world, but I do want to say that this result is very promising, and it does mean that Mamba is possibly something that we should explore, which may potentially replace transformer or be combined with transformer to make our models better. So this is all I wanted to talk about. Again, I want to give credit to Maarten a lot on the amazing visualizations I've been using. And I also watched Yannick's video on Mamba and I learned a lot from him. So feel free to check those resources if you are interested to learn further. Of course, there's an original paper that everything's very detailed. You can look at that. I was at Vienna in ICML last month, and I noticed Mamba 2 is also out in their poster session. I haven't read through it yet, so maybe next time I'll be talking about that. Thank you. And if you have questions, please post it in the comment section. I'll try my best to answer.